Sure that we put the recording on. Yeah. Okay, and then we go to the air server. It's here. Okay, and we start with Cahoots. Number 10 is here, right? Yeah, okay. That's okay. Play. There are no 86 people in this room, right? So maybe the live stream is doing it in some magical way. I have no clue. Gewoon doorgeven. Okay, yeah. That's well. Anyway, I'm happy. Welcome that via they are also participating. Yeah. Okay. Before starting doing any calculations, eliminate those who cannot be true. Yeah, okay, pretty okay. If you look at the object, then the largest mass moment of inertia is clearly about the y-axis. So you should find an answer where the largest number is the y one, and then there are two possibilities, and then you just calculate one and find the solution. Okay. This is an easy one, I guess. Or not. Yeah, discuss it with your neighbor. Convince him. Yeah. Okay, pretty simple. So this is about the Euler equation of motion. You have to take the sum of the torques about a certain point, and also the center of mass is calculated at some particular point of the body. Then the question is, for which specific point is this only valid for? That's a bit disappointing result, and what is the reason? Well, you see in chocolate letters only valid, right? So, and if you read and you think, oh yeah, it's valid for the center of mass, of course. But there's also another specific point for which it would be valid, and that point is a space-fixed point. That's also mentioned. Point of application is non-valid. But if I say only valid, then none of the three answers are correct. So you should say none of the above, because you should know it's either the center of mass or a fixed point. Yeah. Okay, this is a bit easier. So we have a rigid body, and we of course, it can rotate around the three axes, but now we say, well, we just fix the axis. We say, this axis, it's rotating about this axis. What is the mass moment of inertia? So just one number should come out. You have all the time to type it in MATLAB. No problem. You have enough time to start up MATLAB or your calculator. You can also start by eliminating numbers which you think those can't be right. Now, there can be two reasons for why there are so many incorrect answers, right? Either you're unable to perform calculations, that holds for me a lot of the times, or you have no clue how to calculate it. So the first I cannot resolve, the second I can say. So if the axis is fixed, and this is the mass moment of inertia, then you have to post-multiply and pre-multiply this inertia matrix with this direction vector. Or in physical terms, if this inertia matrix is multiplied by this unit vector, you get a torque in space. But we want, for that torque, we want a projection on this axis. So we have to pre-multiply then with the transpose of this. And then we project all the torque which we calculate on this axis. Or in other words, to project the mass moment of inertia, you have to post-multiply and pre-multiply with the transpose. And if you do, and this is a unit vector, of course. And if you do that, then the correct number turns out to be 124. Well, that's how it is. Okay. Already the last question. And that's about the topic of today. And I will be frank, I always have trouble with this, with the order. I always think that I know it, and then, oh no, the other way around. Yeah. So clearly we need some lecture today, right, on the topic. So I'm not going to explain it now, it's during this lecture. Okay, feedback. Yeah. I'm still offline, sorry for that. Then we go here. Yeah. I don't know. Okay. So today's topic is these rotation matrices and the Euler angles. And last week we looked at the Euler equation of motion, right? So the Euler equations of motion in 3D, that's the most important extension we have, is that we say the sum of the torques, and let's say the center of mass, is mass moment of inertia times angular acceleration plus angular velocity times I omega. If you look at the equation, then the elements are torques applied to the body, mass moment of inertia matrix, angular acceleration and angular velocity, and I see no angles here. That's sort of strange. I mean, the only thing which is there is an angular velocity and an angular acceleration, and the whole concept of angles is not in the Euler equation. So then the question arises, do we need angles? I mean, if the equation, if they're not in the equation, we apparently don't need them to do the dynamics of a rigid body in 3D. Before we answer that question, I like to go back to a thing which I forgot to show last week, and that is a book. Two pages from a book, I guess. And the pages are this. Where are we? Lecture 10. Yeah. So these are the Euler equations of motion, right? Which we've seen. Now, somebody derived those equations of motion, and that guy was called Euler, right? Do we know? Have you ever seen a picture of Euler? I have somewhere a picture of Euler. Where is my Euler? Yeah, is this Euler? Yeah, Euler. This is Euler. Let's make it a little bit smaller. Yeah. Interesting guy, right? Polymath. He was good in everything, in math and in engineering and all kind of things. If you look at the picture, it looks rather peculiar, the things he is wearing. Well, what is the first thing you notice when you look at the picture?
Being on his head.
Head, yeah? His head? Okay. Second thing? What do you see? There is something with his eyes. This one is all sort of blackened, and you see this one. Well, what is the unfortunate story with Euler? He was very productive, but he became pretty early in his career blind, slowly. So, but he was still very productive after that. And how did he do that? He had two persons, two helpers, one reader and one writer. So he did everything verbally and everything in his mind. Maybe that's why he's so super smart. Look at the dates, 1707, 1783. How old was Euler when he died? 70 something, right? Same for Newton, which was a little bit earlier. He also almost 80 years old. In those days, what was the average age of people? 40, yeah? Nothing more. So what do we learn from this? Doing mechanics is a very healthy profession, right? You have a long, prosperous life. Okay, so back to his book. He wrote a book, and in the book, of course, he wrote the Euler equation. I mean, it's his equations. And what was his native language? Nah, not Latin. His native language was not Latin. Where was he born?
Austria?
No. He was born in Switzerland, Basel. Yeah. So his native language was a sort of German. But that language, of course, you didn't write in your native language. So the lingua franca was Latin, right, in those days. Now, I don't know how good your Latin is, but my Latin is very bad, but that doesn't matter. Because this work you can easily read. Just skip all the words you don't know, and then all the words you do understand, they will make up together with the symbols, yeah? So in this work, he presents his Euler equation of motion, and they're at the bottom here. And at first you would think, what is this? They don't look like the thing we've written down here, right? Well, during the time, notations changed a little bit, but in essence, it's of course the same. So what is he doing? Nullum, what is it? Nasitur momentum. Oh, momentum pro hoc axe. I know, that's a torque about an axis, right? Pro axe autum IB, well, I don't know, a momentum. And now we get it. Z times dm times d dx dt squared. You see this notation we understand. Already in those days they were using the d for differentiation and so. And that's pretty quick after Newton, because Newton was the guy who, together with Leibniz, independent, they came up with this whole work about differentiation. But Euler quickly adapted that, and the whole notation is what we now use today. Z is a distance, dm is a piece of mass from the rigid body, and ddx dt squared is the acceleration of that part. So this is like the inertia force times the arm. That's a torque about an axis. And then he says, yeah, but this dm x double dot gives also a torque about the other axis, y times dm x double dot. So if you have a point mass and it has an acceleration in a direction, you get a torque about this axis and you get a torque about the other axis, about the two axes. And then he continues explaining how that all works, and then he says, so if we have one axis, then we have to take plus z times y double dot and minus y times d double dot. And also for the other two axes we get that. So finally, he then writes down his equations of motion. He says, well, the sum of the mass times the acceleration in the x is the forces in that, and for the y and the z, so he recaps the Newton equations, and then these are the Euler equation of motion. Of course, he didn't substitute the expressions for the accelerations. If we would do that, we would finally get our equation here with our strange thing. But this is basically the Newton equation, Newton Euler, which we can easily read. Okay, back to the question. I was just postponing, because I don't know what the answer is here. So we see the equation, we see no angles, still we have the feeling we need angles. Why do we need angles? For that we have to dig deeper in. How do we calculate this thing, this mass moment of inertia about the center of mass? To know that, we have to know what the attitude of the body is. Because this is the mass moment of inertia expressed in the global coordinate frame, and the orientation of the body really matters about what are the numbers here, right? So we need angles to calculate this guy, and we also need angles to calculate the torque, because the torque, we have to express that in some coordinate system, and it's a forces applied to a body, so we have to know what the attitude of the body is. Okay. So it's sort of hidden in the equation. How do we do that with attitude? Well, if we have some rigid body, and we usually draw a potato, right? Then there is some coordinate system which is glued to that body. And for the coordinate system, we have a curly letter. I usually use B. And then that is in reference to some inertial frame that's glued to the ground, and I use as an indicator for that frame N. Why? Well, because Heike started with N. I don't know. It's like the inertial frame. Then we have three axes, and for now I really want to write down independent of x, y, and z. I want to say we have three directions. And it can be x, y, z, but for now I want to use 1, 2, 3. And I want to indicate that these are the base vectors. So this is base vector 1, this is base vector 2, and this is base vector 3. Just in the inertial frame. Of course, in our mind we say, oh yeah, that's 1, 0, 0, 0, 1, 0, 0, 0, 1. Those. And likewise, these axes, initially we usually align it to this frame, then we have these same ones, which we then this one E1, and I use a prime, and the prime has nothing to do with a differentiation, but it's just because it is of this body fixed frame. So I have these three things. Then somewhere in the body I have a point P, and if I want to find what is the position of point P, I write a vector like that, and so let's put a name. There's a P. Now I'm not interested in translation. On purpose I drew the figure apart from here, but I'm only interested in the change in orientation. Officially, if this is point C of the center of mass, you should say, well, the position of point P is the position of C plus the position of C with respect to P. Now, I find the whole translation not interesting. I only want to look at, so this is the translation. and I only want to look at the rotational part. And that is this vector, which I now just indicate by p. Well, this vector p we can write in terms of components. As long as I have p is always p, and the vector is always the same. The moment I say in which coordinate system, I get components or I get coordinates. But I can work my whole math on Euler equation and whatsoever. I can do sort of coordinate free. At the end, if I want to have numbers, I have to say in which coordinate system do you want to express it. Or in other words, if I want to work in MATLAB, I have to put coordinates, numbers. Okay, so how does that work? Well, this vector p we can express in terms of these base vectors. And so we say that's p1 times e1 plus p2 times e2 plus p3 times e3. That's the way it usually works. You say coordinates work like you go first in this direction, then in that direction, and the third step is in that direction. That are the steps you are taking. And then what do we write? Well, if we work in components, we say, well, the components we can also put in a vector, p1, p2, and p3. And this is what you use in MATLAB. These are the numbers you use. They are the coordinates of the point expressed in some coordinate system. So to differentiate between the vector which we haven't expressed in a coordinate system and the components, we have to differentiate between these two. And we then write now this curly letter on the left top to say, hey, these are the components of the vector p expressed in the n frame. So the vector is always the same. These are the components. Now, what we want to do is we can express this point p either in this coordinate frame, in the absolute sense, but we can also express it in this body fixed frame. So we can also write for point p, that is p1 accent, e1 accent, plus p2 accent, plus p3 accent, e3 accent. Or in other words, the components expressed in this body frame are then these p1 prime, p2 prime, and p3 prime. Now, why would we do that? What is the big advantage? What is so special if this is a rigid body? So this is a rigid body. What is so special about these components? Yeah, they're constant. So these are constant for a rigid body. So, but we are not so interested actually in the components in the body frame. Well, they're constant, that's nice, but we are interested in the components in the inertial frame because Newton equations are expressed in an inertial frame. So all the calculations we finally have to do is we say, well, in the inertial frame, the acceleration is this, or in the inertial frame, the angular acceleration is that. So we have to find a way to go from these to these. And of course, the key, the sleutel, is in how do these base vectors relate to each other? That's going to be the key factor. And that's the same which you see in the picture. I mean, if I draw this potato, I have here these base vectors, and here the other base vectors. And clearly, the different position of these base vectors expressed in this coordinate system, these different orientations, they give the relation between the difference in orientation. So that is the way we go about. But first we have to find a way to go back to 100%, to find a way to extract from a vector these components. And that way is actually super easy. So if we have the vector here, the vector p, and we want to know, for instance, component number 1. How do we do that? Well, then we take our base vector 1 and we do the dot product with the vector, and then the result is p1. Why? Well, this dot product is actually, so then we write down this equation, No. No, that doesn't work. Oh. Yeah. So we write it here in the equation, and then we have to take all the dot products. So this dot product, this dot product, and this dot product. But of course, the dot product of E1 times E1 is 1. Yeah. So it's P1. Yeah, 1 times P1 plus, and the dot product of this one is 0. They're orthogonal. So 0 times P2 plus 0 times P3. Because, of course, we have EI dot product J is 0 if I is not equal to J, and is 1 if I is equal to J. And they are, in math they always say they are orthogonal, but I would say they are orthonormal. Although that's not accustomed to say. And I like orthonormal because if you take the product, then the result is 1. The length of the thing is 1. So they have a unit length and they are perpendicular. Okay, so that is the way how we can extract components. And likewise, of course, we can also extract the P1 prime by saying, oh, I take the E1 prime times the vector P, and then I extract that P1, etc. for P2 and P3. Now, nothing much learned there, but the thing becomes interesting when I say, well, you know, I want to know a PI vector, a PI component, meaning I'm going to multiply with EI, but for the representation of the vector, I'm not taking the one in the inertial frame, but I'm taking the one in the other frame. So I write it as P1. Oh, that's not a nice P. Go back. Yeah. P1 prime E1 prime plus P2 prime E2 prime plus P3 prime E3 prime. So I want to know the component in the inertial frame, and I write the vector in the body fixed frame with the components. And now I get all these dot products, but note this EI times this, the others are not 0. I mean, these are different vectors. They are not all orthonormal. Look at the picture. I mean, one axis is like this and the other like that. So we get then all these dot products. So we get finally EI times prime 1. And then I want to write it as a vector product, P1, P2 prime, P3 prime, yeah. And then the second one is EI dot product with the second one, and then EI dot product with the third one. And of course that is for the I, so for all three I can write that out. So finally I get my expression P1, P2, P3 equals, and then a big matrix, and then I get P1 prime, P2 prime, and P3 prime. And what are the entries in the matrix? It's all the dot products you can think of. And so, of course, it starts with E1 dot E1 prime. And then the second one is again E1 dot E2 prime. And then E1 dot E3 prime. And here we have E2, E1 prime, E2, E2 prime, E2, E3 prime, and then E3, E1 prime, E3, E2 prime, and then E3, E3 prime. And those are actually all the dot products you can take if you have these three vectors here, and you make a combination of 2, then these are all the 9 combinations you can make. And since we like this index notation, so we can easily write Pi is EI dot EJ with a prime times P j prime. And for clarity, I and j are 1, 2, 3. And actually, the mapping which I wrote here is the thing we are seeking. Okay? So it tells us, these components, I have a matrix Rij times P prime j. And this guy we then call the rotation matrix. Rotation matrix. Or in other words, this rotation matrix Rij is Ei dot product with Ej prime, by definition. And if we then go back to our handy notation about coordinates expressed in a frame, then we could say, okay, this vector components expressed in the inertial frame is a rotation matrix N, B, and these are the components expressed in the body frame. Yeah? And then this matrix R and B is then apparently equal to these Ei dot Ej prime. So we find the entries. Okay. 9 numbers, so apparently orientation can be described by these nine numbers, right? How do we find the inverse? So we want to sometimes to go back the other way. We want to say, I have it in the inertial frame, and now I want to know what the rotation matrix is from the inertial frame to the body frame. So the big question is, what is this guy? How do we find that? Well, a very quick way would say, well, look at this equation, and then you just take the inverse of that matrix, right? So apparently that is equal to the inverse of this matrix, RBN. Super simple. However, you could also do my whole projection thing the other way around. You could also say, you know what? I'm going to find my Pi prime, taking my I prime, times, and then I express my components in the inertial frame. So I get Ej and Pj. That's also legitimate. And then I get all these dot products. But there were only 9 dot products, so I mean, apparently there's a strong relation between this and this one. So I come to the conclusion that this inertial matrix, if I compare it to this one, the only thing which changed is the prime. Where I have a prime here at I have here the prime at j. And then when I look at the matrix, I come to the conclusion, apparently this rotation matrix Rij, if I want to take the inverse, that is apparently equal to the transpose of the matrix, because the only thing which happened was that I changed the I and the j. I interchanged those two. Or in other words, if we have this one of these mappings, for instance from the body frame to the inertial frame, and I want to know what the inverse is, then that's simple, the transpose of this matrix. And that is then the transformation from the inertial to the body frame. So that is a nice relation. If that is true, then if the inverse is the transpose, then we could also say, and for simplicity I now drop all these indexes, we can say, apparently R transpose times R is the identity. Right? Okay, what the consequences of this is, we're going to see after the coffee break. Okay. Dit zou je me toesturen, weet je nog?
Ik dacht dat ik een USB-stick mee zou nemen. Sorry, dan heb ik de mail niet goed gelezen.
Maar dat werkt toch niet, dus, want het is allemaal een beetje fiebel. Wat wil je doen?
Ik dacht misschien, ik weet niet, misschien kan het anders via hier.
Maar we hebben daar toch beeld achter ons? Dat zou moeten lukken. Ja. En wat wil je laten zien?
USB-stick die in. En dan is het, kijken.
Nee, zullen we maar niet doen, hè. Ja?
Inputters die slide mee. Die is het.
Ja, maar het maakt alleen maar uit er niet hier nog gaan. Ja, precies, maar bij de datum is het meestal nee. Iemand
Ga je gang.
Ja, we hebben verder al het bericht opgestuurd in de Ik wilde alleen nog even een reminder.
Oké. Ja. Maar dan wil je je stick terug. Redden?
Ja, aan het eind.
Nee, maar ik kan hem ook nu geven, toch? Ik denk niet dat hij daar erg zenuwachtig van wordt. Oh nee, daar wordt hij wel zenuwachtig van. Ja. Oké. Dan aan het eind, ja.
We zaten nog een veergrid te kijken van de komende huishouden.
Ja.
Alleen die is hetzelfde als huis met
Nee, ja, de
rubriek.
de rubriek is nog steeds. Ik heb geen tijd gehad om het aan te passen.
Oh, oké, dus dan moeten we even nog een keer.
Dat ga ik vanavond pas doen. Dus ik zit helemaal zo.
Dat u het weet.
Ja, nee, ik weet het. En het staat vanavond op mijn lijstje. Maar, en qua rubriek wat je voor punten krijgt, het is zo'n beetje hetzelfde stramien als met de vorige huiswerk.
Nou, dat komt wel goed.
Dat komt toch goed, toch? Maar wat ben je actief, zeg?
Ja, hij was het eigenlijk.
Oh, oké.
Een vraagje over voorbeeld.
Ja.
Die worden dit dan geleid en uiteindelijk dan dit. Maar ik zie die termen allemaal samenvallen, maar waar gaan deze termen naartoe? Worden ze...
Die lost ze op. Gewoon echt zo. Gewoon weg.
Oh, op die manier. Oh ja.
Het zijn de statische momenten. Want kijk, al deze dingen. De versnelling is constant, heeft niks met i te maken. Dus die mag je eruit halen. Dan krijg je integraal i accent dmi. Oh ja. Nou ja, dat is het center of mass, dus dat is 0. En die ook. Nou, en die valt tegen die weg, want x keer y is y keer x. Dus die is ook weg.
Oh, oké. Ja, dus vooral omdat het statusmoment
Ja, als je dus niet zou doen, dan krijg je extra termen hier.
Ja, nee.
Ja?
Waarschijnlijk niet dan dacht ik.
Nee, is niet erg, is niet erg. Ja. Oh ja. Nou, dat hebben iedereen wel gezien. Ik ga even proberen of ik mijn stream kan fixen.
Ja, we zouden nog een afspraak maken om over het BMX'en verder te praten, maar ik kan ook gewoon een mailtje sturen als het makkelijker is.
Maar altijd even op maandagmiddag langskomen, dan is het allermakkelijkste. Ja?
dat wij eigenlijk daarvan slaap zijn. Nu heb ik het niet uit.